And while you do that, let me introduce myself. I am Megha. I will be going over the introduction notebook for the Jupyter Lab, explaining basics of how to set up or how to configure your account and use APIs for simple examples. And my colleague Jonas will be explaining, taking you through a little more complex applications. So you are a pro at the end of this workshop.
Also, if you get stuck at any point, you can just raise your hand and I'll come by.
Yes. So if everybody has already connected to the internet, then we shall begin. So please go to this website, dataspace.copernicus.eu. This is the URL for our platform, which has data analysis tools and also ways to access or download this data as well. How many of you already have an account on this website? Oh, a lot of you already. Okay. I saw that a few hands were not raised, so we will go through the login process or registering process very briefly. So if you click on login, you will find this button, register. You click here, and you will have to put in your first name, last name, email, password, these information. And the most important thing is to accept the terms and conditions. The other two, it's okay if you don't. And if you click on register, you will get an email to activate your account, and then we can begin. So I have already logged in. How do we get to the Jupyter Notebooks is by going to Analyze Data tab, and here you will find Jupyter Notebooks. Please click here, and you can access the Jupyter Notebooks. There are multiple server options. We'll choose a small server because we are not doing many crazy things today. For using all the Jupyter Notebooks, we first have to have credentials, the Sentinel Hub credentials. For that, you would have to go to Sentinel Hub under Analyze Data again. Click here, and you will come across your dashboard with the processing units allotted to you and things like that. Go to the user settings and create a new OAuth client. Now you can name your client. I will name this CDSE workshop and create client. Make sure to copy this somewhere safe, because once you close this pop-up window, this is not going to appear again, the client secret. So we copy this. And I will close this now. And here you can see the client ID as well. So I will copy this as well. Both of these are very important. So now we are here in the Jupyter Lab environment. Jupyter Lab is an intuitive interface where you can do your scientific analysis as well, use the terminal or have text file. Basically, it helps you to code more easily. So let's begin a terminal, and we will copy what we had earlier, the GitHub repository. I don't know if you all saw that before, but I shall type it again. Git clone. Okay, he got there. Once you do that, the repository will be cloned. And you will have a folder called BiDS CDSE Jupyter on your left. Please double click on that. And we shall go to the first introduction presentation. Here, there is a little bit of introduction about Copernicus data space ecosystem and the Jupyter Lab. There are links to documentation that you can find more. But my colleague has already given quite a good introduction to Copernicus data space ecosystem. So first thing that we have to do now to run the notebook is to change the kernel to Sentinel Hub. If all of you are here, please change this and select the kernel Sentinel Hub. Once you do that, we can start running the notebook. We will import all the libraries that we need for this notebook first, and then just now we did this process of acquiring our credentials, the client ID and client secret. So the next thing that we do here is to run this cell where we will be prompted to put in these credentials, what we just downloaded or extracted from the dashboard. So I shall put in, so the client ID starts with SH. And client secret.
What is the client ID?
Client ID, we just got it on the dashboard. It is here. This is very small, I think. Sorry. Just a minute. Yeah. So when you create a new client, right under it, you will get the client ID. Just copy this. And the client secret is what you got in the pop. Yeah. So after running this cell, what happens is your credentials are saved with the profile name CDSE. If you want, you could change this name and save it as something else. So when you run it locally, it would be saved, and you can just call that with the profile name instead of typing in your credentials over and over again, which is not a good thing. So now we can move on to the next step. First, we introduce the Catalog API. Catalog API is a application program interface that helps you to understand the availability of data. So it lets you know what data is available, what is the temporal extent, what is the processing done for the data, and all of this information. And it follows the Stack API specifications. So you can find the links to documentation and API definition here in the Markdown. And let's begin to configure the catalog. Once you run this cell, you will get information about the API itself. So its ID, it is called the Catalog API, and it has all the information about the API itself. So once you configure this catalog, we can now start to see what data is present in the catalog. At the moment, we have Sentinel-1, Sentinel-2, L2A, and L1C, Sentinel-3 OLCI, Sentinel-3 SLSTR, and Sentinel-5P level 2 data already. So for now, I have only displayed the ID of all the data collections. So there is a little task for you. Could you try and display what the title or the description of these data collections are? The tip is to replace just one of the components of this request, and you can see it. Let's try this out, a small activity. Yes, please just change one of these. So basically you have to change the ID to request for another part of this request. So say you want the title of the data collection, you would have to replace that with ID. Or if you want to see the description or the providers of this data, then you would have to replace that in the request. That's what you have to do. Just to know about the data itself. You would see a list of this information about each of the data.
They are also metadata.
Yes, they are all from the metadata. Yeah. If you have been able to do that and not get any error, then we move on to the next. We will then look at a particular collection, get more information about one type of collection, say Sentinel 1, A with extra wide acquisition mode. We can request for this data collection just by mentioning the code over here. You will find what each of the data collections are called in the documentation. So let's try this. You can, once you request it, you will get information about what the data is, description about it, then the spatial extent, the temporal extent, all the metadata about the collection itself. And if you want to request the data from a particular location, just a small bounding box that you already know, and you know the dates and like the time range that you want your data in, you can define that. Here I have defined Venice, like a small bounding box around Venice. I have put in the latitude, longitude. You can change this to whatever you want. But let's run this request now. So we have the bounding box, we have the time interval, which specifies dates from April to September of 2023. And then in the search iterator, we mention what is the data that we are requesting. This is data collection Sentinel 2 L2A. And then we mention the bounding box, the time interval, and we apply a filter. So cloud cover is a major obstacle in multispectral imagery. So we would set this cloud cover to less than 5% to filter out all the other acquisitions. And in my output, I would only want to display the ID, the date time, and the cloud cover percentage. So this is the request I'm trying to make. And once I do that, I get all the list of acquisitions that meet this criteria. So we have 33 acquisitions that meet this criteria within this time range, and we can see the information about that. So this means that our area of interest has some data with the less cloud cover that we like, and everything is great. Now we can start to request this data. There is a question there. Yes?
The question is the cloud coverage calculated on area of interest or the whole tile?
Whole tile. The cloud cover is, maybe we can use the mic so it would be heard in the recording as well. The question was if the cloud cover is calculated just for the area of interest or for the entire tile. It is for the entire tile.
Where this information is taken from? From the metadata of is the level 1C of the quality metadata
Yes.
from the level 2A?
No, this is L2A.
So this information is taken from the metadata of the level 2A.
Level 2A,
The
yes.
quality, so the one after the atmospheric correction process, or from the metadata?
From the metadata
But the metadata is
built on L1C.
Yeah.
So it is, okay.
It is L1C.
So it's not from the sync classification of the level 2A?
No.
Okay, thanks.
It's not. So to request for this data, how to access it is using the process API. Andres already gave a small introduction to process API, but essentially what this does is you can define what kind of input is considered and how you want to process this, create a visualization or create an index, put in your workflow and request the results of it as a TIFF image or a PNG or just a statistic. No, you can work with it to get the result that you want. Our process request will contain two parts. First is the eval script. There is a little bit of explanation over here. So the eval script is a piece of JavaScript code which helps us define the input, the output format that we need, and what has to be done to the pixels. So what kind of processing happens to these pixels. Here, for an example, I've considered a true color eval script. So this takes in the band 2, band 3, and band 4 of Sentinel 2L2A data, and it gives me output, a 3-band output, which is a RGB composite output. And I'm taking the output over here, which is the band 4, band 3, and band 2, just a true color image. This is the simplest, a simple eval script that just gives us an image in true color. So again, we go to the request. This part of the request is called the request payload. Here you mention the eval script that you used to process the data, and then you input, you mention the input data collection and the time interval, and also a new term we encounter here is mosaicing order. So when we look at a bounding box, it might, the tile that we select might only cover half of the bounding box, not the whole thing. So we need somehow to fill up the whole bounding box using mosaicing. So this stitches two tiles together, and the criteria in which these two tiles or these two tiles are selected is mentioned here, defined here in the mosaicing order. For this request, I have set it to most recent. So that means since my time range is from April to September, so if there is an acquisition on 1st of September, then that would be the acquisition used, no matter what it is, even if it is a very cloudy image or if it is not that great, it would still be selected. So let's run this request. Oh yeah, and I mentioned the bounding box. The resolution that I've selected is 20 meter by 20 meter. And another important thing is where you save the data. If you want this data to be saved locally, then you can mention the path to the folder where it is to be saved over here. Then we run this. So this, sorry, I did not run the previous cell. So this defines our request for now, but it has not yet been requested. So let's, with this, the next cell, we see that the request is made, and you have to set this save data to true to make sure the data is saved. And then the image is plotted together. So everything is happening at the same time. And you can see the image. This is pretty cloudy image of Venice. Yes.
Where the request is executed, on server side or on client side?
On the client side. This is just for the client. Like, it's just whatever you are processing, it is done locally. Or right now it is Jupyter Hub server, but if you're doing it locally, then it's on your account. It's on the client side. Yeah. So we see a pretty cloudy image. And next is another task for you. You can try to write up an eval script that gives you a false color composite imagery, which uses the band 8, that's the near infrared, red band, which is band 4, and green, band 3. Try this. Try to write up an eval script which is similar to the one that we saw before, but replace the bands. And then also run the request by setting the mosaicing order to least CC. That way we get the least cloudy image as a result. I already have put in the solution here. If you click over here, you can see the solution, but try to do it without seeing, and then if you have any questions, we can work together. So I'm going to cheat a bit, and I'll just copy what I've written before. And I get this image. Um, this is a pretty cloudless image. You can also change the visualization if you want. You can modify the eval script, set it to true color to see Venice in the true color, natural color. So this was a simple RGB composite that we created. We can also visualize indices, the remote sensing indices, in using the eval script. Next, we will try to get a normalized difference water index over Venice. So what this means, basically I will create a mask. I will not even display the index. I am trying to create a mask of water bodies around Venice. So what this is taking as input is the band 2, band 3, band 4, and band 8. And the NDWI is defined as a normalized difference of band 3, which is green, and band 8, which is near infrared. With this index, you can set a condition. If the index is above 0, that means it's water body. You set the color to 0.5. You can change this. You can set it to NDWI to display just the index, or like visualize the index, or just keep it as a blue color mask. And if it is not water, then the true color would be displayed. So we run this eval script. And in the request, again, it's the same as before, except we change the eval script over here. We change this eval script, we set the mosaicing order to least CC, and resolution is set to 50. I'll change this to 20. And I run the request. We see this kind of a image where all the water pixels are classified, are displayed in blue color, and the land is displayed in true color RGB composite. Next activity for you is to display a normalized difference vegetation index. So for this, I would ask you to use all the things that we learned today. So we change the bounding box. So I would like you to define a bounding box and the time range of your choice. I've just given an example over here for the bounding box, and I've used the same time range in the solution, but you can change that. And you can display the normalized difference vegetation index, which is mentioned here in this expression. There is solution here again. You can try it without looking, but if you find any trouble in between, please take a look at it. So define your eval script and define the request and try to visualize this. The NDVI basically gives you values in the range from -1 to 1. And over here with the request, if you run this request, you will see that the bare soil or areas with lesser vegetation are almost black or gray, while regions of higher vegetation are almost white or really bright pixels. So we see a part of a forest over here with really high NDVI, and there are few agricultural fields with different in different growth stages of crops. So this is a grayscale image. I'll go through this request a little. So in the eval script, you can take in the input of band 8 and band 4, and you display 3 or 4 bands, and define the index as normalized difference of band 8 and band 4, and return index in all 3 channels, RGB channels. That way we get just the same value for all the 3, and it gives us a grayscale image. Now, I can keep it here. So to wrap this up, we learned how to configure our profile with Sentinel Hub credentials, and we understood how to use catalog API and the process API to request information about the data and the data itself, and how to process this as well on Jupyter Lab. Next, we will see a little bit of example, a use case which uses the pollution statistics of different European cities, and it would be explained by my colleague Jonas.